Hi, this is Mikhail Golovnya, Senior Scientist at Salford Systems. What I'm going to do in this short video is I'm going to discuss stability of Carted trees, and in particular stability of Carted trees when you build a binary classification problem. Just as a reminder, when Cart grows an individual tree, what it's trying to accomplish in the case of binary classification problem, it's trying to find rules based on what it's seen in the learned sample that isolate one class versus the opposite class. So the ultimate goal is to find a hierarchical structure that separates records belonging to class 1 from all the records belonging to class 0, and it does it with varying degree of success. Now the problem is that the algorithm, as it builds the tree, only sees one part of the data. We call it learned sample. And as the tree gets larger and larger and larger, nodes are getting smaller, and at some point you may see that based on the learned sample, you have a very high concentration of the events of interest in any specific node. Unfortunately, it may not hold on the test sample, and some people call it overfitting towards learned sample or learned sample bias or things like that. Therefore, there is always this problem of finding the optimal balance in the tree that kind of generalizes the tree best in terms of how it behaves between the learned sample and the test sample. Again, in some cases, it's not necessarily something that you will be concerned with, because in many situations, the whole reason we're building a Carted tree is to run some kind of nice partitioning and find out what the underlying story is, and you might be interested in optimizing overall misclassification cost, things like that. But in those situations, when you really want to have a tree that is nice, balanced, and stable, some of the machinery that's available in SPM will be of great help. So let me go ahead and illustrate some of these topics using a real live run. What I have here is SPM running, and I will use the data set that I often use in our training sessions, known as a spam base. So in other words, we will try to separate spam emails from non-spam emails. So I'm opening a spam-based data set, has 4,601 emails that are roughly divided into half as spam, the other half as non-spam. I'm going straight into model. I'll work with Cart engine. I'll sort the data in file order, and the binary target has a name target. All the other 57 predictors are used to try to separate spam from non-spam. And if you've never seen that data set before, the predictors describe each email in terms of word frequency, and it's generally known as bag of words approach in text mining. And there are some other videos when I elaborate on this data set a little bit more. But in this case, we're just working in binary classification, single tree. I am going to partition data set into 50% learn and 50% test sample. So in those balancing situations, this is often a very good approach, because in this case, I know for sure that my available data set is divided exactly 50-50 into learn and test. And therefore, whatever I see on the learn sample, I want it to be confirmed on the test sample. And in many cases, whenever you build a single tree, you want to decide on some reasonable limits on how large the nodes are allowed to be. So in this case, I'll require at least 30 records in the parent nodes and at least 10 records in the child nodes. That's it. So it's a very simple Cart setup. I'm going to proceed with building a single tree. The tree comes back. And by default, Cart optimizes relative cost or expected misclassification rate. And the optimal tree is shown as having 18 nodes. Now, at this point, I am not interested in optimizing my cost. I'm more interested in seeing how well the tree and individual node level generalizes between learn and test samples. And one way to see it is if you look at the summary display and go under Terminal Nodes tab, then you can see all of the nodes in the upper half sorted by learn sample responses within each node. So it's always decreasing, as you can see here. In the bottom half, it shows response rates in the test sample for the same set of nodes. And as you can see, there are situations here, most notably node number 15, where the learn sample shows very low response, but the test sample shows very high response. And those are precisely the situations that we are somewhat unhappy about in terms of presenting this tree. Now, to show you that that does not necessarily happen all the time, if you look at a much simpler tree, let's say the tree that has only 5 terminal nodes, and again you click on the summary, look at the terminal nodes, now you see that pretty much there is a reasonable level of agreement between learn and test samples. So as the tree grows bigger and bigger, somewhere at some point within the tree sequence, there is that divergence that takes place, and we're interested in finding that point within the tree sequence. Now, this is a toy example, so there's not very many trees to work with, so conceivably you could go and do it by hand. But it gets more and more awkward as you go into larger data sets and more splits, and it's kind of, there is always need to automate such things. And this is where the machinery of train versus test consistency comes in. All you need to do is press on this button here, and what CART does, it automatically scans every tree available, and summarizes consistency between learn and test in this upper table here. So you can scroll it, and as you can see, these are trees indexed by the number of nodes, 5, 6, 7, all the way up to the largest tree. And each tree is shown whether it agrees or disagrees. Now, agreement is the green color, disagreement is yellow. And there are 2 types of agreement or disagreement, based on direction and based on rank. Now, in this case, basically both types of agreement measures show consistent results. In some other runs, you may see that you may have a directional agreement, but not necessarily a rank match, and so on and so forth. Now, first of all, let's see what it means. If you look at the 9-node tree here and double-click on this row, the same node performance tables that we looked at previously in summary reports now shown on this graph. And what this graph demonstrates is that pretty much all nodes based on learn or test performance fall on as either having positive greater than 1 lift or less than 1 lift, and that's normally what we're looking for in those consistency reports. Another way to look at it is if I go back to my tree, my summary, the navigator window, click on the 9-node tree as suggested by this report over here, and then look at its summary. Under terminal nodes, I see this display here, and now all of the nodes are pretty much consistent, and that's the same display in terms of lift that's shown on this graph. Now notice, if I, on the other hand, pick the next available larger tree that shows the disagreement, in particular a directional disagreement, then when you double click on that, there is a 1 node, specifically node number 8, where there is a directional disagreement in terms of lift between learn and test samples, and this is why that tree is marked in yellow color and discarded. And again, another way to look at it, if you go to the next tree, look at the summary, and the terminal nodes display, now this node number 8 is clearly sticking out. And the table shown here summarizes the entire tree sequence so that you can quickly zero in on which tree is stable and which tree is not. Now notice also, and let me close all of these windows here, notice that the agreement or disagreement has some of these thresholds. So if you lower a threshold, it's almost like the level of fuzziness that's allowed on the level agreement or disagreement. So for example, if you lower the threshold on agreement in terms of rank, at some point you'll see that at this point some of these smaller trees are reported as mismatching on rank. And what it means is when I double click here, there is this node number 3 that's kind of out of that ordered sequence of nodes based on the learned sample. The way the rank matching order is defined is that once you sort all nodes based on learned sample lift, you want to see a test sample lift in approximately the same order. Well, in this case, some nodes are mismatched, and therefore it shows as a mismatch. However, if you increase the level of fuzziness that's allowed on that matching process, now you can basically still declare them as match, and only when you go to a much larger tree, now you have some very fundamental mismatch that is no longer allowed based on the current level of fuzziness. And by the way, at the bottom here, it shows for the currently selected line in the upper table, it shows what happens at the specific node level, so you can quickly focus and zero in on some of the specific nodes where that mismatch is taking place, and it kind of gives you nice additional information on what to look for. And you can also manipulate some controls here that are pretty much self-evident, switch between class 1, class 0, and so on and so forth. So hopefully at this point you see how easy it is to look at the entire tree sequence, and using this learn, test, consistency, quickly analyze it and find the exact point within the sequence where a specific tree starts mismatching between learn and test samples. And there are two measures of mismatch, one based on direction, whether you have a lift that's greater than 1 or less than 1. And there is also a more stringent requirement, the rank order match, where not only you require the same direction of agreement, but also the same sorted, ordered sequence. And those are very useful things that sometimes come in play. So next time you work with a very large data set and you want to build a tree that shows very nice consistency between learn and test partitions, with a few clicks you should be able to identify where in the tree sequence that specific tree is available. In the next little segment, I'm going to show yet another example where this tree consistency also interacts with some of the splitting rules, and you may find it as an additional interesting extra trick that you may run when you do these types of analysis.